Hello, welcome again. We are covering the subject thermodynamic for civil services, mains, IFS, and various gate exams. And we are studying the chapter second law of thermodynamics. In this, the next topic is Carnot cycle. So, Carnot cycle is an ideal cycle in which all the processes are reversible, and that's why it is also called reversible cycle. So a reversible cycle is a cycle in which all the processes are reversible. So now we will study the Carnot cycle, and in this the first process is your isothermal heat addition or reversible isothermal process. So we will consider piston cylinder arrangement. So this is your piston in this cylinder, and in which a gas is maintained. So during this process, a diathermic cover is placed here, and through which heat is supplied, that is your Q1, and this diathermic cover supplies heat at a constant temperature. So here heat is supplied at constant temperature, or it maintains a constant temperature condition. So if Q1 is the heat supplied and some work is also obtained during this process, so W12 is the work, and if the gas is not perfect gas, then there will be change in internal energy, because for an ideal gas only there is no change in internal energy when isothermal process is maintained. But if there is an non-ideal there is a non-ideal gas, then there will be change in internal energy. So Q1 is equal to U2 minus U1 plus W12 is your first law. If ideal gas is there, then U1 will be equal to U2. Okay. So here, if ideal gas is there, then all the heat supplied will be converted into work done. So now this is the first process, and it is carried out by maintaining the diathermic cover. So after heat addition, there is second process that which is called adiabatic expansion. So to maintain adiabatic conditions, we have placed here adiabatic cover already. Now we will replace this diathermic cover with this adiabatic cover. This is new. Okay. And now the expansion will take place and no heat will go into the system, because it is surrounded by adiabatic cover. So expansion will take place at the cost of internal energy. So internal energy will decrease and expansion will take place. So if so here heat supplied is 0, and the first line 0 is equal to U3 minus U2 plus W2. So some work will be obtained. Okay. And now after adiabatic expansion, again there is an isothermal process in which heat is rejected, and this is carried out by placing the diathermic cover again. Now heat rejected is Q2, and almost constant temperature is maintained if there is an ideal gas within the system. Okay. So for that process, the first law is minus Q2 is equal to U4 minus U3 is equal to, no sorry, minus W3. So W3 is what minus is means work has to be done on the gas. Okay, for an ideal gas, U3 will be equal to U4. Okay. So next process again is your adiabatic process, which is again carried out by replacing this adiabatic cover with the diathermic cover, and here again the adiabatic process which is carried out by placing this adiabatic cover, and in this some compression will take place. Okay. And heat supplied is pure heat supplied or heat rejected is 0. So that process is your 4-1. So final condition is 1 and initial condition is 4. So change in energy is this. Okay. And work is put into the system, so minus W41 will be there. Work is done on the system, so work done is minus 41. Minus means we are giving work to the system. So these four processes are shown on a PV diagram. This is your one to reversible isothermal heat addition. This is your reversible adiabatic expansion, and this is your reversible isothermal heat rejection, and this is your reversible adiabatic compression. Okay. So now in this heat is input, that is Q1, and in this the work is heat is output, that is Q2. So total change in heat is, or net heat that is Q1 minus Q2, and work is done in all these processes. So it will be W12 plus W23 plus W12, here expansion is taking place, here also expansion is taking place, and here uh, you can see the compression is taking place, and here again the compression takes place. So that's why we have subtracted these work. So net heat supplied is equal to net work. Okay. So this is the piston cylinder arrangement. This cycle can also be studied in here when the fluid is flowing through the power plant. So here in this diagram, this a fluid is flowing through the turbine and the compressor and these heat exchanger. This fluid gets heated at constant temperature in the heat exchanger A, and then it is fed to a turbine where it does some work on the turbine, which is WT, and again then this fluid is transferred to second heat exchanger where it rejects heat, and then it is fed to compressor where it is WP work is done on it. So this is the schematic diagram of Carnot cycle for steady flow process. So this is your Carnot cycle. In this two isothermal and two adiabatic processes are there. And during isothermal process, heat addition and heat rejection are taking place. Okay. And during adiabatic process, expansion and compression are taking place. However, during isothermal also some compression and expansion are taking place, but main heat addition processes or only heat addition processes are isothermal, and only heat rejection processes are isothermal.